parallel as well as resistors in series. The two formula are quite familiar to all of you, but over here we're just trying to show you how to derive the formula based on Kirchhoff's laws. So let's consider two resistors connected in parallel. Now every one of you know that we're going to derive to this formula 1 over R equals to 1 over R1 plus 1 over R2, where R is the equivalent resistance of the two combination. Okay, R is the equivalent resistance value of the two in parallel. Now, from the first principle, we know that the current at this juncture here, at this junction, is the sum of I1 and I2. Now, the voltage, since the voltage is the same for both, we can express the current as a ratio of voltage to the resistance. Okay, sorry. So this in fact is I equals to I1 plus I2, and I is simply V over R, and I1 is simply V over R1, and I2 is V over R2. And substituting these terms and cancelling away the V's, you end up with this equation. The combined resistance value of the two resistors is given by the inverse of the sum of the inverse. Now you notice that if you combine these two resistance, if you solve it out, you'll find the combined resistance is actually R1 R2 over R1 plus R2, or you can write it in terms of ratio of R1 R2 times R2, or R2 over R1 plus R2 times R1. Now you notice that the ratio here is always less than 1. Okay, the denominator term is always greater than the numerator term. And this implies that the combined value is always less than either R1 or R2. Okay, because the combined value is number less than 1 multiplied by R1 or multiplied by R2. So it's always less than R1 and R2. So this is a useful check whenever you have to calculate resistors in parallel. The final value must always be less than any of the component resistance value. Let's move on to look at how we derive the formula for resistors that are joined in series. Now, from second principle, we know that the rise in potential equals to the fall in potential. Now we're going to for the current in this case is the one that is common. The current through each of the components is the same. So we're going to express the potential in terms of the product of current and resistance. Okay, where current is the same for both. So for the combined resistance, supposing this is equivalent to a combined resistance with the same current, so the left hand side term E can be represented as I times RC, and each of the component terms B1 is replaced by I times R1. So cancelling away the common term I, you end up with combined resistance equals to the sum of the two resistance values. So of course from here you can see that the combined resistance is greater than R1 and greater than R2 because it's the sum of R1 and R2. Let's look at more examples. R1 and R2 in this case, they are connected in series because they have the same current. The current can't go anywhere. After passing through R1, the same current must go through R2. Okay? What about this circuit here? R1 and R5, are they in series and in parallel? Well, no matter how you connect the battery, you can put a battery here. The current at this junction will branch into two, and then they'll recombine back. Okay, or you can choose to place the battery at another location. You can place a battery anywhere. In fact, say you put a battery here, it doesn't matter. You will always find that R1 and R5 is parallel to each other because the PD between this point and this point is always the same. Okay. Now the same cannot be said for R1 and R4 because R1 and R4 are quite separated by resistor R5 and so on. So they're neither in series nor in parallel with each other because the currents are not the same, the PDs are not the same. Okay, let's look at the last example on this type of problem here. Now, these three resistors R1, R2 and R3, they appear to be connected in series. But in fact, they are in parallel. Now, how do you see this? Now, remember this is a piece of wire. It's a piece of wire. The same piece of wire is... This is another piece of wire. Now, so this point and everything here until here, they have the same potential. And this point, all this have the same potential. Okay? So I can keep R2 at the same position. And I can in fact turn this R1 around, bend it around, imagine, and shorten this top section of the wire to here. This is my R1, and R3 originally is here, can be turned around in a similar way because R3, this potential is the same as this potential. So I can bend R3 around, and therefore R1, R2, R3 are in fact parallel to each other. Okay, let's look at the 5 resistors in parallel. If you apply the formula for resistors in combinations, 1 of R equals 1 of R1 and so on, R1 plus R2 and so on, any number of times, and if the resistors are all equivalent, you just divide by the number of parallel components. In this case, it is simply 1 ohm. Okay. Let's look at question 6. Resistors that are connected in a triangular fashion. Right, find the resistance between X and Y. Now there is another point Z. This point Z is a distractor. You don't have to worry about this presence of this point Z here. So what you do in the calculation is you take 2.5 and 5 ohm and treat them as a series combination. So these two are to be added together, and then after adding up these two, you can treat this as a parallel combination with 2.5. This is how we arrive to this formula. Let's move on to the next example. For circuit X, the first thing you do is you take the 4 and the 3 ohm resistors in series first, and then you sum up the parallel with the 2 ohm. That gives you 1.56. And for circuit Y, a similar way, you sum up the two resistors, this time in parallel, 4 and 3, sum them up in parallel first, then we add to the series resistors of 2 ohm. Now for the last circuit, you can easily see that all the 3 resistors are in parallel with each other. So after working out the values, you can find that the resistors in order of increasing resistance is in order of Z, X and Y. Okay, this one looks complicated. Example 8. The resistance looks rather complicated, but what we normally do is solve the combination from inside first. Okay, so what you do is you sum up the 2 ohm and 3 ohm, and that gives you 5 ohm. And the 5 ohm and the 4 ohm are actually connected in parallel. So this is the series combination, and this is the 4 ohm in parallel with it. This is the parallel. This is the 5 ohm on top and 4 ohm in parallel, and this is in turn in series with the 5 ohm here. So this 5 is for this term. Okay, and this upper branch here, the entire 5 is 5 plus this whole lot here is in parallel with the 6 ohm. So as you can see, you do it step by step from the internal portion of the circuit, and you easily derived, simplified it to get the combined resistance value. Okay, that's all for this section here.